All right, so we are going to start our study of polynomial functions in this video, and we've actually looked at several examples of polynomials without maybe knowing what a polynomial is. We're going to see that, all the quadratic functions we just looked at and all the linear functions and constant functions are specific cases of polynomials. Okay, so there's a lot to unpack in this one section here, but we're going to see the polynomials are going to be rather nice functions because they would they're next to a quadratic function and a linear function. These are the nicest functions that we can work with. So a polynomial function, or simply a polynomial, is a function of this form where we have a constant times the power of x plus another constant times another power of x and so on, where the only restriction is that this n has to be a non-negative integer. So it can't be a fraction, it can't be negative, and then all these a's are going to be real numbers or real constants. Okay, so the thing to remember is that all the powers of x have to be non-negative integers as well. If this a sub n is not 0, then we say n is the degree of the polynomial. So it's to find the degree, you look for the highest power of x if the polynomial function is in this form. So it's the highest, and by highest power we mean the highest exponent that you see. So that's the degree. Then this a sub n is the leading coefficient, and this term a sub n times x to the n is the leading term. If all the terms are 0, if all the coefficients are 0, then this is just called the zero polynomial, and we don't really give it a degree, or we say the degree is negative infinity. As a specific case, we see that non-zero constant functions are polynomials degree 0. Non-constant linear functions are polynomials of degree 1, because for example, 2x plus 3. Okay, that's certainly a linear function. We can also see it's a polynomial where a sub 1 is 2 and a sub 0 is 3. Okay. Quadratic functions are polynomials of degree 2. Okay, so if we have something like 3x squared plus 7x plus 10, okay, a sub 2 would be 3, a sub 1 would be 7, a sub 0 would be 10. All the exponents as I said, all the exponents of x in polynomials must be non-negative integers. And that means, of course, no fractions. And the domain of a polynomial, well, we can basically plug any number we want to in for x, right? Because we're just plugging in a number and raising it to a positive integer. So the domain of the polynomial is all real numbers. Right? Because there's no square root in there, and there's no... we're not dividing by anything. So the next thing about graphs of polynomials is that they are always smooth and continuous. Okay, so there are no vertical asymptotes, there are no breaks, there are no corners, there are no open circles. They're just very, very nice, smooth. So obviously, we look at a parabola. Okay, well, that's smooth and continuous. A line is smooth and continuous. But we're also going to look at, graphs that will look like this with several turning points. All right, and the thing here is that if a polynomial is in this form where the powers of x are decreasing, we say that's standard form. We're going to see that there are going to be other forms of polynomials, but this is what we mean by standard form. So another way you could think of this is that the degree is the highest exponent of x, so you see if a polynomial is in standard form. So if we look at some examples of polynomials here, these first two examples, I think we can see that these are both in standard form. In part A, this is the highest power of x. Okay, the highest exponent is 3, so the degree is 3. Here, the degree. This is a polynomial. The fact that we have a fraction here as a coefficient, and then here we have pi square root 2, it doesn't matter about the coefficients. They just have to be real constants. The important thing is that the exponents of x are non-negative integers. So here the degree will be 4. All right, now in this next example, it might not look like a polynomial if you see something like x minus 1 times x minus 4. But if we multiply this out, we get x squared minus 1x minus 4x is minus 5x, and then this is plus 4. Okay, so sure enough, this is a polynomial, and it's a polynomial of degree 2. In part D, we can see that we have x minus 2 to the 17th. Now, we don't necessarily have to multiply this out to find what the degree is. We only have to know what the highest power of x will be. And we can see that if we were to have 17 factors of x minus 2 all multiplied together, what would be the first term that we would get? Well, we just x multiplied by itself 17 times. So this would be x to the 17th, and then plus some other terms that we don't know. But this, we do know that this is going to be the highest power of x, so the degree is 17. And we can use that philosophy down here. Here we can see if we were to multiply this all out, okay, we would have x squared times x cubed times x squared. Okay, so this would be x to the 7th plus something, right? We don't know what the other terms would be, but we know that the highest power of x would be x to the 17th, because basically we take the highest power of x here times the highest power of x here times the highest power of x here. Okay, x squared, x cubed times x squared, that's x to the 7th. So the degree is 7. And then this last one, what would the degree be? Well, the highest power of x is x to the 1st, so that's 1. Don't be distracted by this pi squared. Okay, pi squared, that's just the coefficient. Okay, we want the highest power of x, so that the 1 is right there. All right, now these functions are all polynomials. But then there are some functions which are not polynomials. Okay, the part A, this is not a polynomial because of this -1 here. And in part B, this is not a polynomial because of this 3/2. That's not an integer. Here we can see that as soon as we see with 2 over x, that's going to be the same thing as 2x to the minus 1. Okay. Okay. So the function is really x squared plus 1 plus 2x to the -1. So this is not a polynomial. You can also see that the domain of you can't plug 0 into this function, right? So the domain wouldn't be all real numbers. So that's why this is not a polynomial. Once you see an absolute value, you know you won't have a polynomial because there are no absolute values of a polynomial. This is actually the absolute value of a polynomial, but it's not a polynomial. Here, again, these are absolute values, not polynomials. And if you look at the part F, this is a little bit of a tricky one, but yes, you might think, okay, this when you square a square root, you get x, and you might think that this is equal to x plus 3. Okay, but these are not equal as functions, because if you plug in -1 here, you get 2. If you plug in -1 here, you get something that's undefined. You can't square something that's undefined, right? Okay, so these actually are not equal. These agree when x is positive, but if x is negative, they're different. This is defined. This is undefined. Okay, so that's why these examples would not be. These functions would not be polynomials.